Okay, thank you. Yeah. Cool. Right. The penultimate part of the course. In the course, I think it was billed as trustworthy computing, but I wanted to talk about trustworthy systems. It may have been called trustworthy systems, but I'm going to talk to you about a program of work that follows on from the work that I've just presented in the last hour or so. And this work is called Building for Resilience, okay? So the first thing I want to do is for us to consider risk. Does anyone know an equation for risk at all? No? Anyone know? No? An equation for risk, any idea what it might be? What is the risk of something happening?
Loss.
Sorry?
The amount of loss if something occurs, like if attacker does something on the system.
Right, so the amount of loss, that's impact, yeah? And what do you need to multiply that impact by? You said if an attacker. How do we measure the if bit? Okay, well actually what we do is the most basic equation is that, yeah? How likely is it to happen and how bad is it? Yeah? It's not the only one. There are others that you can use, and I use some others as well. And you can break these down, likelihood and impact, you can break them down. But basically, risk is likelihood times impact, okay? So, a number of years ago, the director of the National Cybersecurity Centre was giving a talk. I'd met him before, we'd been chatting. I work in this area, and he said, he told a public audience, he said, it's not when, if you'll be attacked. So if, you said the if. So it's not about the probability of it, it's when. So basically saying you will be attacked. Yeah? Now for certain things, not for everything, what people have started to say is stop with the uncertainty. Stop saying it's 10% likely. Because how do you even work out 10%? Yeah? So they're saying, forget that, because actually, based upon historical data, your likelihood is often 0, 0, 0, that's 1, because it's happened. So there's been a move to say, stop saying uncertainty, forget that, let's just manage by the impact. Because just because something's more likely, right? Imagine I work on, and I still do work on likelihood and impact.
Likelihood maybe 1 or approximately 1.
Approximately 1, yeah. But what they're saying is, just imagine it happens. So if likelihood is 1, then your risk is just the impact, right? So that's what they're trying to say. Now the thing is, so I still work on likelihood as doing likelihood, but the thing is, imagine a timeline here, right? And as time goes along, yeah. Now you've thought that the likelihood was 50%, and the likelihood of something else was 80%, was 1%, yeah. Now the thing is, likelihoods don't happen over a time. The likelihood is uniform. So over a given, perhaps infinite time, the likelihood of something happening is 1%, yeah? But it could happen, just that 1 in 100 times could happen tomorrow. The 1% incident could happen quicker than a 50% incident, yeah? So this gives us a problem because you've not worried about the 1% incident because it's unlikely to happen. Yeah, so people are saying for really important things, consider the likelihood to be 1. Okay, so I just want so what we're thinking now is that starts to get us to thinking, okay, if we are going to be attacked, if the likelihood is 1, then there's no point just thinking about protection and security. What we need to do is, if we are going to be attacked, we need to think about resilience. We need to make sure that we are at a point where we can recover. So these detect, understand, and act is very important. Okay? Very important to remember that. Okay? Okay. So the first thing is, yeah, you're trying to protect first, but when there's an attack, you need to be able to detect it. And I can tell you, when I did the UK Security Breach Investigations Report for UK government in 2010, the average time that an attacker was in the system was 18 months. So people have got their systems, back in 2010 this was, and that figure stayed the same for quite a while. I don't know what it is today, but 18 months people had some kind of control. They were sitting in the network, exfiltrating data, doing little things, but people did not detect it. Yeah? Once you detect it, you've spotted something's gone wrong, you've got a good intrusion detection system, then you need to understand what it means. And this is important in a breach, right? This can cost you a lot as well, because you need to understand what's been compromised, what are attackers doing, what are they going to do next? Yeah? So first of all, you need to know that they're in the network, or the system, sorry. Then you need to understand what they're doing, because if you don't understand what they're doing, how can you act appropriately, right? So you need to detect, understand it, and then act appropriately. Because what you don't want to do is detect, then act, and you've done the wrong thing, right? Because actually what they wanted you to do is the action that you've just done, yeah? So a simple thing might be, you know, you might turn off all the systems because you detect that you've been breached, and the attacker goes, brilliant, that's really what I wanted you to do, yeah? So gather information and find what are they trying to do, so that you can act appropriately. So this is a project called CyRes, Cyber Resilience. It's conducted with a range of universities in the UK, and there are 4, I showed them yesterday, National Cybersecurity Centre Research Institutes. So the Research Institute for Trustworthy Interconnected Cyber Physical Systems, RITICS. There's the one on Institute for Hardware Security. There's one for verifiable and trustworthy systems, and there's one for socio-technical. So all of those are in. It's led by a good friend of mine called Peter Davies at Thales, and I'm one of the key people in it. And what we're trying to do is look at the evolution. So if we think here is a timeline, yeah, what we have to do when we're breached is detect, then understand, and then act, and do all of that before you get what's called catastrophic failure. And that's why in these critical national infrastructure things, we say, let's not think it might not happen. Because if you say a 1% chance of happening, you're saying 99% it won't happen, right? So let's not think about that. Let's try and understand. Let's imagine that an attack is going to happen. Let's make sure that we do the act, the appropriate act, before we get to catastrophe, okay? So I told you a little bit about connected autonomous vehicles in the last session. So what we've got now is we move connected and autonomous, right? First of all, connected means rapid communication with other vehicles and infrastructure, yeah? And automated means it can do things on its own, so quickly as well, okay? You can have a connected vehicle that's not autonomous, and you can have an autonomous vehicle that's not connected, yeah? And there can be different degrees of each. But what happened with old cars that you used to have, and many that, you know, my family had years ago, you had a very bounded scope. You knew what was going on. You knew what the car could do. You knew who owned the car. It didn't have lots of different components. That bit that I just mentioned about Volkswagen and Bosch, and then other new entries who come in, you know, in a Tesla, you've got Mobileye, might provide the software. They may also provide hardware, but it could be someone providing hardware and someone else software. Then you've got the communications chips and things. So system ownership is now not known. You know the interactions, right? Because when we've got AI in the system, I talked about at the start of this course, you can have systems where you've got a very, very large input space and a large output space, and in the middle, you've got this complex black box. So you do not know the interaction. So this is where we're getting to the unknown interactions. We don't know how these parameters that go into the black box, how they affect each other. Yeah? You also could predict things quite well, what will happen, yeah? Because it wasn't quite as many parameters. And now we're getting emergent function, and the AI changes, so we've got some software over-the-air standards, actually, some SOTA standards, but we've got to try and understand that. And we used to be benign intent. There was no intent to try and corrupt. But now, because of it being a cyber element into the critical national infrastructure, there is nefarious attempt. So what happens is, where we used to have something called the engineering V process, yeah, the V process is about how you develop vehicles or other engineered systems. It's about system capture, it's about validation, it's about hardware in the loop. That cannot work for all operating conditions because of these changes that we've got. Yeah? So the system is becoming what we call limitlessly boundless. Yeah? We can't predict what the machines are doing, and therefore we're having to be really adaptive. So what it used to be is a car, so I mentioned Jaguar Land Rover and Rajin Tata. At the early days when Jaguar bought that company, yeah, it would take from the idea of a vehicle to getting it on the road 7 years. Yeah? How many of you think it takes 7 years nowadays? No. Can you imagine how far behind the technology curve a car would be if it took 7 years to go from initial concept through to production on the road? Yeah? So it's happening much quicker, yeah? But also because of the changes, because of these changes, yeah, you're going to have to start doing this V instead of in 7 years. It's going to have to be really quick. So there's commercial pressures, but there's also security risks. Was the hand up now? Just a stretch. I thought you put your hand up. No. Okay. Right. So now this is the important thing now that I want you to think about. And this is important about scale, and this is why cyber attacks can become so rewarding, and ransomware attacks, they're so rewarding, because you can do them at an unprecedented scale. Yeah? You can do them remotely. Yeah? If you wanted to tamper with a vehicle before, you had to go with a screwdriver and things like that. In fact, you needed lots of skill, right? Now, there is cybercrime as a service. So what we've got is some major changes, right? So what we used to be able to do, because it's when it was unconnected and manually controlled, electromechanical, it was different to the connected and automated digital systems, right? Because you could test for the failure modes, because there was only certain things that a car could do or would do. Now you can't test for all failures anymore, yeah? Because it's so complex. If you failed once, yeah, you could say, how often would a tire blow out? And you can still do that today, right? You can say, oh, it's going to happen, you know, there'll be one blowout every 1 million miles traveled, or 10 million miles, or whatever it is, yeah? And that's the thing you can say, because that's predictable. When you've got AI and when you've got an attacker in the loop, yeah, we don't know. Sorry, where was I looking at that? We don't know, can't necessarily just fail once, because with the AI, you could fail globally. Yeah, if I break the AI, that means I break the AI in all Teslas right now. Remember that thing with the Jeep? 1.4, all of them had to be replaced, not just one, yeah? And we don't know when, so it can fail globally and unpredictably. For the original one, each attack takes expertise, but you can, once you've learned to do something, yeah, you can replicate it because all the other cars are quite similar. It might be a protocol attack, so you don't need to do lots of different learning. And finally, each system needs a separate attack, but now you only need to succeed once because it's all connected, and you end up with catastrophic failure. Okay, so what we propose in our system, yeah, is that what you do is you monitor the system. So if you're monitoring, that's helping you to detect, right? So this is where we fit. How do you do that? Detect, understand, and act. What you have to do is monitor the situation, and then you have to simulate. So simulate helps you understand more about what's going on, and you can also simulate the best solutions to overcome that problem. Yeah? So you can, what you do is you simulate this attack that's going on because you monitor it. You say, okay, well, what is going to happen from that attack? You can run lots of different scenarios, by which stage you understand the attack more because you can see what it can try and do. Yeah? So this might work in like something called a digital twin. Yes, you run it in a simulated environment. You then say, well, how do I stop those? You run a number of different mitigation strategies, and you look which one did best. So you're playing these games on it, yeah? And you say, which one went best? Yeah? Once you know which one goes best, you can then deploy the best outcome to help you mitigate the problem. So, what we do is we monitor in real time, we monitor abnormal events that are not considered within the design limits. So you've got these design limits for a system. Yeah, these are the standard operating boundaries that you want to work in. Yeah, if anything's outside of that limit, yeah, so it's not that it's not working now, it's not had a failure that's catastrophic, but it's not working as designed, as expected. Yeah? So what you do is you're monitoring for that, and if it's not in there, you detect this as normal events. You then observe the emergence and propagation of potential new threats. So what you're now doing is also not just observing the vehicle, but observe the environment. Yeah? And if you think this is what, we proposed this quite a few years ago, and we're going to do some work to update and publish it soon. But that's what happens when people look at mobile banking. They're looking at what happens on lots of different things. It's what happens in the zero trust architecture, isn't it? Yeah, at this stage when we first came up with this zero trust architecture wasn't as big as it is now. Yeah. But we were saying even then, look at that cyber threat intelligence, yeah? Look at how it interfaces across the system boundary. I've just shown you a reference architecture, yeah? What we're talking about here is cyber resilience, and we're really talking about central to that, the connected autonomous vehicle. But what we're saying here is look at those system interfaces. Look at what's happening elsewhere, gain that intelligence as well. And the reason that we do this monitoring, yeah, so collecting loads of data, is we can support the mitigation plan deployment decisions if something goes wrong. So what we're doing is and I think I've seen a couple of you in this room who've done work on early warning, yeah? What we're doing is early warning, getting ready to get everything ready in case there's a problem. So don't wait until there is a problem, monitor, and if there is, yeah, your detecting is going to be quicker, but also maybe your understanding. Yeah. And in fact, what you're preparing for is the action as well. And what you do is if you keep doing this, as you run exercises, as people do try to compromise, and they do, yeah. The thing is, a lot of compromises are not catastrophic. Yeah. If you're learning continually from those, you can feed them into better plans. Yeah. So what we do is highly automated real-time methods, yeah. But at this stage, what we're proposing is to keep a human in the loop. In fact, the way we would keep a human in the loop is human reinforcement learning with human feedback. Because what we're doing is, don't forget, with all this simulation, we're playing games, we're playing scenarios. That scenario knowledge can be used to develop games that can be used as the reinforcement learning game, right? So you can take those simulations that you're doing in real time and say, okay, how do I react best? What are the sort of games? But instead of just doing it to select your one measure, use it to create a policy for next time, yeah? So, and you'd update and you'd run a number of different policies against that, okay? One thing that we think there's a few things that are important is using something called theorem proving to decide is what you've got within the design limits or not. Cryptographic techniques to make sure that the data is reliable and trustworthy, and having actually interrogating the system, yeah, instead of being passive and listening to the system as it goes, actually having some interaction with the system to see that it is still performing the way that you would expect. The simulation element is a multi-dimensional simulation of all relevant aspects of the system. And what you do is, we talked about, again, reinforcement learning wasn't quite as big, but using game theoretic approaches. So reinforcement learning is sort of playing games anyway, it's just slightly different because of Nash equilibria are not needed. So what we do is we simulate the high level, so like the CAN bus, the data bus, and the low level compute cycle. So we're really looking at the whole system as relevant. And this can provide an understanding about possible future events. So as I said, setting up these policies. And what it can help you is to help do predictions, yeah? What's the likelihood that you're moving, you know, and you could just use sort of, not statistical methods, but you could use numerical simulation methods, right? So some numerical integration to say what's happening with where I'm going, how far am I going off? Am I increasingly degrading performance, or is performance going level? So it will give you an idea how long, even if it's not correct, it will give you an idea how long until you get to catastrophic failure. Yeah, okay. And then deployment of mitigation plans needs to be time critical, so it needs a big set of network intelligence here. And what you need to have is consider reconfiguration of some or all of products or their components. And what helps us now, we're very much software defined in systems now. Okay. So I'm going to go through a little bit of some of the, I might come back to, oh yeah, okay, so this bit's important, because this is where, you know, we talk about network intelligence, and it's actually maybe about a digital twin. But what you do is you monitor and known threats go into your intelligence, right? So your monitoring is the cyber threat intelligence that I mentioned. It's also details about your specific vehicle. You could use, and this wasn't really used because we came up with this before Google released federated learning, but you could use federated learning here, right? But basically get this network intelligence, yeah, send scenarios to the simulator and the best outcome, yeah, and have this back and forth about the guidance and expected outcome. So what we really proposed is network intelligence is important to sit aside this, that involves monitoring, simulation, and deployment. So I think I've covered that, because what I want to do, here's one thing that I want to say. What's really important is we need to think about the design and operation. So we can do a lot of this testing now, especially because we've got such big compute power at the design stage. So we could do some things, but we don't want to throw away the existing great work we do in design, right? Can't just do everything at high compute levels, and we need some of the formalities before. So this is definitely required for operation, but for design, what you want to do is have you design for the adequate operation in the shortest possible lead time, right? So what you do is your monitoring it's got cyber monitoring, real-time system and deployable plans, but what you're doing is moving between design and operation of launching the vehicle. So this says, you know, what you want to do at the design stage is take all of this information that you might run, all of the simulation, feed it into your design stage, where you know that there are bits that it's not going to change, yeah, still use this V model, but in a collapsed time, but build it up with this system that allows us to predict what's going to happen. I'm just going to go on to 3 more techniques for you. And these are the reason that I put the screen up. So, what you've got is this is time passing through here, okay? At this time, there is a threat, and actually it shouldn't really say threat, it's an attack. Yeah, so this is exploited. It's no longer a threat, it's exploited, right? So what happens is somebody has released something into your system. That's a time capital T, right? Now what happens is when that happens, it's going to take you some time, let's call it T sub delta D, to detect it, yeah? Now if you've got a really good intrusion detection system and it's a wild anomalous thing, great, you might be able to detect quite quickly. If it's something called an APT, advanced persistent threat, then that might be much more difficult, because what you've done is you've made loads of little attacks, and there's nothing really to have noticed until the last piece of the jigsaw becomes much more serious. But that's the time to detect is T underscore D. Then you've got some time to understand, yeah? And then you've got some time to act. You need to make sure that between this time and catastrophic failure, whenever that is, and I'll tell you what catastrophic failure is, that you've done the detect, understand, and act. So therefore, for complete cyber resilience, you need these 3 to be less than TC, this distance from here. Okay? So, let's consider what a catastrophic attack is. Now, I told you that what we've got is, what time is it now? 4:12. Yeah, and I need to finish at 4:30, right? So I've still got to, yeah. Sorry. My watch was upside down, that's why. It's still on UK time. I'm getting very confused. Sorry about that. Right, okay, so we've still got time, so no worries. Right, so what you've got is catastrophic failure, and think about this in vehicles, but it could be other things, is this. If you've got lots of connected autonomous vehicles around the streets, what would be really bad, yeah, is if all of them completely corrupted, yeah, so it's complete corruption for all vehicles, yeah? Agreed? So what we do first is we create this thing saying, you know, when you've got, what is the drop in number of units that you've got, yeah? And what percentage operation have you lost, yeah? So this is actually a strange diagram, so I'll show you on here, yeah? What you want, yeah? So I'm just going to do it here. Percent of systems, in this case vehicles, down. Yeah? So how many, so obviously you know, the worst case is 100%, yeah? And when there's no attack, you're at 0%, everything's working fine. Here's where you will be normally, right? It's everything's great, no systems are down, and here you've got % of performance loss, yeah? So how are they underperforming, yeah? So here you've got no performance loss and no systems loss. Brilliant, yeah? Now where you don't want to be is in that corner. That means absolutely everything has gone, yeah? Now then, what you need to decide is, where is catastrophe going to happen? So what you might say is, look, actually, a point that's here, which is half of the vehicles are 10% degraded. You might say, well, that's a catastrophe, that's going to be bad, that too many vehicles at a certain level. So what you need to define, yeah, is how many vehicles and how many, what percentage, yeah, because that's 100, remember? And you say all of this area, that is catastrophe, okay? So what we start with first is we say, hang on, how much operation can you lose? Yeah? So a service that fails in all instances, even only for a low % of operating conditions, is not resilient. Yeah? Then we say, a service that fails only in some instances, and only for a low % of operating systems, is still not resilient. Yeah? So what we're talking about is, well, actually in here, yeah, catastrophe is this corner, but I think catastrophe can be wider. It's up to you to define where it is. You could push this all the way to the top and push this all the way, well, some of the way. But for me, yeah, instead of this, you can call this. That's up to you as an individual, what you think is catastrophic. But in any case, there are things that are catastrophic that you need to prevent. Yeah? So, finally, the question becomes, how many times, yeah, how long is it catastrophic for? So, imagine, so this is why time is a factor as well. Imagine that you've got, for a split second, the cars aren't working, right? Well, actually, if it was a split second, you might say, well, that's tolerable, right? Yeah, I don't know. It depends upon the circumstances. It depends what you classify as catastrophic. Yeah, but if a car is unavailable for a day, whole day, then you're in trouble. Or if it's forever, you're in trouble. So what happens is you want to increase, you know, so when you've detected the system, you want to maintain the number of operating systems that you can do. You want to maintain how much each is operating, and you want to make sure that it's happening all the time. Yeah? So, what we have is this. What we want to try and do is, if there's a probability curve over time, we want to make sure that we are getting better at detecting. So basically, what we want to do is push this up so we get better probability of detecting in a shorter time. So if you push this curve up, it means that this particular time your probability of detection has increased. Yeah? So that's what we're trying to achieve. We're also trying to do the same for understanding. We're trying to understand quicker. Yeah, so this is probability of understanding is time of d plus u. And then finally, we've got the time to act. Yeah, and the time to act is if you keep deploying solutions quicker, then you've actually understood, detected, and acted quicker. Okay? So what we're trying to do in this system, yeah, is we are trying to say, and I probably could, I didn't think I'd have enough time for all of this, so I can tell you a bit more. But what we are trying to do is ensure that we detect faster, understand quicker, and act more frequently. Yeah? And this leads us to, I'll just tell you, the principles. Frequently. So the way that we can do this, yeah, is yeah. So the important thing we've got to do is create what we call proactive updates. Yeah. And what we want to do is make sure, so proactive updates will make sure that that frequency is disrupted. Because if you are proactive in your updates, if you keep updating, what you're doing is every time an attacker studies a system, yeah, if you update it, then they have to go back to the drawing board and relearn the system. So what we're saying, if you want a more resilient system, do managed but frequent updates. The next thing we say is, if you want to stop the number of operating units, if you want to lower that, what we have done is worked around creating what are called engineered differences. Yeah. So what we're proposing, instead of, when I said you've got global failure, if we have engineered differences, so we create systems, yeah, that are different. So let's say you have the same functionality, but you can create it in 10 different ways. Yeah, that means an attacker could compromise a system. He gets a vehicle, compromises it, but it will only work for 1 in 10 because the other 10 are engineered differently. Yeah, so we are introducing uncertainty to the attacker. Yeah. So our process of engineered differences means that we don't get this case, because what we noticed is you break one Jaguar Land Rover machine vision system, you break all of the systems. So that is what we've been working on in cyber resilience. It is complex. Some of it is happening right now. So what we've already seen is this network intelligence piece starting to come in. There was a proposal from the government that they would create a national capability for this. The problem is, how do you move between the public and private sector, right? Because the government can't just provide a service that monitors all of the vehicular systems, because it's a private road network. But what government is looking at is there something we should have where we incentivize to do this, and then this becomes a service? As we see more of these attacks that I showed you before, sorry, in the last slide, when I showed you, the last lecture when I showed you lots of different attacks, as there are lots of attacks increasing, then the cost per company to support a national intelligence. So I can tell you 2 companies who could deliver this, who were working on the proposal with me. They are BT, which is a big networking company in the UK, and Cisco. Cisco has got one of the biggest collections of data in the world, right? because Cisco routers are all over the world, right? So if you're thinking about this network intelligence to understand the abnormal events, then who better to see that than Cisco? Also, don't forget that attacks that we see at the network level are not always restricted to vehicular systems. So you might see something in other areas because it's a vulnerability that goes across systems. And if you have someone like Cisco, it doesn't have to be Cisco, but someone like Cisco supporting this, they're going to give you lots of data to support your work. Yeah? So this work continues. People have been developing this idea in the US as well as the UK. And as I say, we're just about to launch a new revamp of the methodology. Okay? Right, it is 25 past right now. I will give you a chance for any questions. I've given 4 lectures today. Yeah, lots of information, sorry. We started off, remember, with synthetic data and privacy in synthetic data. We then went through private data sharing. We've then gone through transport and mobility and ended up with, in an example of transport and mobility, talked about building resilient systems. These resilient systems, if you look at perhaps, which one's best? This one, yeah. If you look at this one, there's nothing in that is specific to vehicles at all. Yeah. So that would be, instead of just the Internet of Vehicles, that could be any kind of connected device. And we have actually applied this cyber resilience to connected devices as well. So I've covered lots, so feel free to ask any questions. But the key things to take away are, well, let's think of them in order. So I talked about, the first lecture was on synthetic data, yeah? And what's important is to think, why would we use synthetic data? What are the key areas that we use it in? And how do we do it? So remember what, why, or how, just at a basic level. On private data sharing, we have to think, how can we do that? You know, what are the different mechanisms we have? And we went through a lot of those for you. On transport and mobility, we discussed a number of elements, talking really about the threats and reference architectures. And here we've talked about cyber resilience. And the big thing about cyber resilience is, you know, to understand, where is it? That if you cannot detect, understand, and act in time, you will have catastrophic failure. And we can't have catastrophic failure in any critical national infrastructure. So we could do exactly the same thing actually for energy systems, power systems, yeah? Okay. Thank you very much for your time. I will see you tomorrow for supply chains, trust in supply chains, and exam. Okay? Take care. Thank you all.
I can try conceptual conflict to resolve.
Go on.
All the conceptual
Yeah.
conceptual conflict I try to resolve.
Okay. Okay. Super. Oh.
Slides and books.
थोड़ा सा लाए बहुत हुआ ना धन्यवाद अभी ये है ना हाँ जी
Hi, Carsten.